All right, hi everyone, welcome. So this week we're going to cover chapter 11, and this chapter is really going to kind of dive into just some more things and information about working with experimental designs. So let's go ahead and jump into it. All right, so like I said, this week we'll be covering chapter 11, more on experiments, and this deals with confounding and obscuring variables. So this chapter is focused on two major concepts. First, threats to internal validity, and second, interrogating null results in experiments. We'll cover each of these topics in detail as we go through this chapter. There are two main sections of this chapter, and the first one discusses potential internal validity problems and how to avoid them. We'll first quickly review the three threats we covered in chapter 10, specifically design confounds, selection effects, and order effects. Then we'll cover some additional or 9 other threats that we'll talk about as well. The second major section we'll discuss describes some of the reasons experiments might yield null results. Did the study give a null result because the manipulation truly makes no difference? Or is the null result due to too much variability within groups or a lack of sensitivity in our measure? We'll go over how we would go about answering those types of questions in this chapter. So let's talk about the first main section, threats to internal validity. So listed here are the subsections we'll cover. We'll talk about an example of a really bad experiment or a tale of what not to do. Then we'll discuss 6 of our new 9 threats that have to do with pre-test, post-test designs. Then discuss the remaining 3 threats to internal validity that can be presented in any study. Finally, we'll cover how to still interpret the value in a study and how to see through the field of problems. Let's start off by describing the one group pre-test, post-test design, also known as that really bad experimental design. You can see the outline of this type of experiment here on the slide. Part A is a general diagram, and parts B and C are diagrams of specific studies we'll discuss. The really bad experiment is also known as a one group pre-test, post-test design, which means that there is only one group of participants who are measured on a pre-test, exposed to some treatment, intervention, or change, and then measured on a post-test. Such a design is problematic because it is very vulnerable to threats to internal validity. The first example study, which is outlined in line B in the diagram, describes Nikhil, a summer camp counselor and psychology major who has noticed that his current cabin of 15 boys is an especially rowdy bunch. He's heard a change in diet might help them calm down, so he eliminates the sugary snacks and desserts from their meals for 2 days. As he expected, the boys are much quieter and calmer by the end of the week, after sugar has been eliminated from their diets. The second example experiment outlined here in line C describes Dr. Yuki, who has recruited a sample of 40 depressed women, all of whom are interested in receiving psychotherapy to treat their depression. She measures their level of depression using a standard depression inventory at the start of therapy. Then for 12 weeks, all of the women participate in Dr. Yuki's style of cognitive therapy. At the end of the 12-week session, she measures the women again and finds that, on the whole, their levels of depression have significantly decreased. Here we can see the results from these two bad experiment examples. It would appear from looking at the graphs that in both experiments there was a change in the groups from pre-test to post-test. On the surface, this appears to be meaningful, but let's now talk about why these studies are problematic and how they can break down under threats to their internal validity. So if you recall, this chapter covers a total of 12 threats to internal validity. The first 3 are design confounds, selection effects, and order effects, which we covered before. These 3 threats were the focus of the previous chapter. Here, we'll discuss the remaining 9 threats out of the total 12. This slide presents 6 of those 9 threats that can all be present when using a pre-test, post-test design, as in our 2 bad experiment examples. These 6 threats are maturation threats, history threats, regression threats, attrition threats, testing threats, and instrumentation threats. The final 3 threats, observer bias, demand characteristics, and placebo effects, are applicable to any experiment, not just ones that employ a pre-test, post-test design. There are also combined threats, which we'll discuss along with each of these individual threats in detail. The first threat listed is known as a maturation threat. A maturation threat is a change in behavior that emerges spontaneously over time. For example, children become better and faster at solving addition and subtraction problems as they get older. Trees grow taller with age, and over time, people tend to recover on their own from various psychological disorders. In a really bad experiment, remember that there is only one group of participants and they are getting the treatment. But in a true experiment, there is a comparison group in order to prevent maturation threats. In the depression study graphed here, a comparison group has been added to Dr. Yuki's really bad experiment. Notice that the two groups are quite similar in their depression scores at pretest, but the depression scores at post-test differ, with the therapy group having lower depression scores than the no therapy group. Thus, the effect of maturation could be subtracted out when interpreting the results of the study, and a maturation threat has been prevented. After subtracting out this maturation effect, if a change is still present, which it is here, then we can say there truly was an effect of the treatment, and that the change didn't simply come from that maturation effect. The next threat is called a history threat. History threats result when some external or historical event affects most members of the treatment group at the same time as the treatment. So it's unclear whether the change in the dependent variable for the experimental group was the result of the treatment itself or the result of the historical factor. For example, suppose you were studying the effects of meditation on stress levels among college students. And while you were conducting the study, a violent event occurred on the college campus at which you were collecting your data. The meditation group did not show significant decreases in stress levels as expected, but was that because the treatment wasn't effective? Perhaps it was effective, but the campus violence raised people's stress levels, which made it look like it was not effective. Another example can be seen here. The figure on this slide shows two graphs from the Go Green study mentioned in your textbook. In graph A, it appears that the experimental and comparison groups both had similar declines in electrical usage from September to November because of the change of seasons. Therefore, it looks like the Go Green campaign didn't actually have an effect. However, in graph B, you can see that the treatment group decreased its usage more than the comparison group. Thus, we can rule out the history threat and conclude that it was the treatment that caused the decrease. Next, we have regression threats. Regression threat is also known as regression to the mean. It's a statistical concept in which extremely low or extremely high performance at time 1 is likely to be less extreme at time 2, or closer to average. For example, if you're in a really good mood or a really bad mood, you'll probably be in a more moderate mood tomorrow due to regression. Regression threats only occur in pretest post-test designs. Specifically, they only occur when a group has an extreme pretest score, either high or low, and you can anticipate that the score of those participants will regress towards the mean at post-test. Regression threats can be avoided by using comparison groups and inspecting the results. If you look at the graph A, you can see that both groups had similar levels of depression at pretest, but the therapy group had lower levels of depression at post-test than the no therapy group. Regression can be ruled out, and we can conclude that the therapy worked. Graph B shows the possibility of a regression threat because the two groups don't start out with equal depression scores at pretest. Therapy group is more depressed. At post-test, the therapy group's level of depression has declined from the level at the time of the pretest, but it's still greater than that of the no therapy group. Therefore, it's not clear whether the decline occurred because of statistical regression or because of the treatment. Graph C depicts the therapy group starting out with higher depression scores than the no therapy group. But this pattern is reversed at post-test, when the no therapy group had higher depression scores than the therapy group. This could not be accounted for by regression alone. Therefore, the independent variable must have had an effect on the dependent variable in this graph. The fourth threat to internal validity in pretest post-test designs is known as an attrition threat. Attrition threat is a reduction in participant numbers from pretest to post-test. So attrition is only problematic when it's systematic. So in graph A, 2 people drop out of the study from pretest to post-test, and those individuals scored at the high end of the distribution, systematic. This decreases the post-test mean dramatically. You don't know whether it was the attrition or the independent variable causing the decrease. However, in graph B, the participants who drop out have scores closer to the mean, so removing their scores doesn't dramatically change the group mean at post-test. Therefore, attrition isn't a real threat here. One way to prevent attrition is that when participants drop out of a study, the researcher removes their scores from the pretest average as well. Another approach is to look at the pretest scores of dropouts. If they have extreme scores, then they're more likely to threaten internal validity than if they have more moderate scores and should be removed. The fifth threat is known as a testing threat. Testing threat is a type of order effect in which there is a change in participants as a result of experiencing the dependent variable, or the test, more than once. Their scores might go up due to practice, known as a practice effect, or their scores might go down due to fatigue, known as a fatigue effect. Testing threats affect internal validity because it's not clear if the treatment caused the change in the dependent variable or whether practice or fatigue did. One way to prevent testing threats is not to use a pretest, called a post-test only design. Another way is to use alternative forms of the test at pretest and post-test. Having a comparison group is also helpful. See the two graphs here. You can rule out testing threats if both groups take the pretest and the post-test, but the treatment group exhibits a larger change than the comparison group. Finally, we have instrumentation threats. Instrumentation threat, also known as instrumentation decay, occurs when a measuring instrument changes over time. For example, observers change their observation criteria over time, or a researcher uses different forms of a test at pretest and post-test, and they're not equivalent forms. One way to prevent instrumentation threats is to use a post-test only design. However, if you need a pretest post-test design, you should make sure that your pretest and post-test forms are equivalent. In terms of making observations, you might retrain your observers throughout the study. Finally, you might counterbalance the order of the pretest and post-test forms, such that some participants get form A at pretest and some get form B, and then they get the other form at the post-test. An important distinction between instrumentation versus testing threats: in an instrumentation threat, the measuring instrument has changed from time 1 to time 2, whereas in a testing threat, the participant changes over the period between time 1 and time 2. I mentioned before that there are also combined threats to internal validity. Sometimes in a pretest post-test design, two types of threats to internal validity might actually work together. Two examples of combined threats are a selection/history threat and a selection/attrition threat. An example of a selection history threat: well, suppose students at one university were in your treatment group and students at another university were in your control group, and say the study was on the effects of meditation on stress. However, during the course of the study, a stressful event occurs on one of the campuses. Now you're unable to determine if your effect is coming from your meditation manipulation, the school, or the event that happened at one of the schools. An example of a selection attrition threat: let's say that participants in one group have to travel 1 mile for the study, and participants in the other group have to travel 20 miles for the study. Well, you might have more attrition in the 20-mile group due to the distance from the lab. So you couldn't be sure if differences between groups were due to the independent variable or the distance and attrition. So hopefully you can see how multiple threats can combine to cause additional threats to internal validity. Next, let's talk about the last 3 threats to internal validity that can happen in any study design. And those are observer bias, demand characteristics, and placebo effects. These are 3 potential threats to internal validity, and they can occur not only in the very bad experiment example, or the one group pretest post-test design, but also in experiments that have a comparison group. Observer bias is bias caused by researchers' expectations influencing how they interpret the results. For example, Dr. Yuki might be a biased observer of her patient's depression. She expects to see her patients improve whether they do or not. Nikhil might be a biased observer of his campers. He may expect the low-sugar diet to work, so he views the boys' post-test behavior more positively. Although comparison groups can prevent many threats to internal validity, they do not necessarily control for observer bias. Even if Dr. Yuki used a no therapy comparison group, observer bias could still occur. If she knew which participants were in which group, her bias could lead her to see more improvement in the therapy group than in the comparison group. Demand characteristics is bias that occurs when participants figure out what a researcher's study is about and change their behavior in the expected direction. In order to control for observer bias and demand characteristics, a researcher can conduct a double-blind study, which is designed so that neither the participants nor the experimenters working with the participants know who is in the treatment group and who is in the control group. If a double-blind study isn't feasible, then an acceptable alternative is a masked design, also known as a blind design, where participants know which group they're in, but observers don't. The final threat to internal validity are placebo effects. Placebo effects are present when people receive a treatment and improve, but only because they believe they are receiving a valid or effective treatment. For example, participants are told they are receiving a new therapy, pill or injection, but in fact it's missing the active ingredient. Or they may be told they are getting a new type of therapy, but in fact simply chatted with someone and didn't get any therapy at all. Nonetheless, participants may improve because they thought they had therapy. It's important to note that placebo effects aren't imaginary. In fact, placebos can be strong treatments. In order to rule out the placebo effect, a special comparison group is used that is receiving the placebo therapy or placebo medication, but neither the people working the participants nor the participants themselves know who is in which group. This is known as that double-blind placebo control study. In the top graph, you can see that both group symptoms decreased. However, the group getting the true therapy improved more than the group getting the placebo therapy, which suggests that the therapy had some actual effect. But is that really a placebo effect? In the graph that we just talked about, there might not be a placebo effect. However, perhaps some of the improvement was due to maturation, history, regression, testing, or instrumentation threats. In order to determine whether there is in fact a placebo effect, the researcher might add a third comparison group that doesn't receive the true therapy and doesn't receive the placebo therapy. They don't receive any therapy at all. If you have a placebo effect, see the graph on the bottom, then the no treatment group should not improve as much as the placebo group. So we've discussed 12 threats to internal validity, and they are summarized in the table on this slide and the next. With so many potential threats out there to internal validity, why do we bother conducting experiments at all? Well, a number of threats described are only an issue in the one-group pretest post-test design. But if researchers design their studies well using comparison groups, reliable coding procedures, double-blind designs, placebo conditions, and control variables, then they can prevent these threats to internal validity. Here we can see the first 5 threats, specifically design compounds, selection effects, order effects, maturation, and history. We just discussed these in detail, but hopefully this table helps to keep them organized and see them presented together in one place. Here we see the remaining threats to internal validity of experimental designs. We have regression to the mean, attrition, testing, instrumentation, observer bias, demand characteristics, and finally, the placebo effect. Let's shift now to discussing the second major section of this chapter, interrogating null effects. What happens when a study finds a null effect, also known as a null result? In other words, what if the independent variable did not affect the dependent variable? So there is no significant covariance between the independent variable and dependent variable. Typically, null effects aren't discussed much in the popular media because they're more focused on effects in which the independent variable does affect the dependent variable. Here we see some of the subtopics we'll discuss in more detail in this section. The 3 graphs in this figure all come from post-test only designs. However, null effects can happen in pre-test, post-test designs, in within groups designs, and even in correlational studies. In graph A, money didn't cause participants to feel happier. Why? In graph B, taking a GRE prep course didn't have a significant effect on GRE scores. Again, why? In graph C, anxiety didn't affect logical reasoning scores. Why might this be? Sometimes when a study has a null effect, it might be that the independent variable really didn't affect the dependent variable. Other times, when there's a null result, It's because the study wasn't designed or conducted properly. So the independent variable actually did have an effect on the dependent variable, but some obscuring factor got in the way of the researchers detecting this difference. There are two types of obscuring factors. One, there might not have been enough difference between the groups. Or two, there might have been too much variability within the groups. Let's look at each of these types in detail. Sometimes the cause of a null result is not enough between group differences. This might occur because of weak manipulations, insensitive measures, ceiling or floor effects, or a reverse design confound. Based on the three examples we just looked at in the discussion of null effects, we can think of them in terms of weak manipulations. Perhaps in the study on money and mood, with the levels of the independent variable being no cash, 25 cents, or $1, that just wasn't enough money to affect people's mood. The difference didn't really matter. Sometimes a null result occurs because the researchers haven't operationalized the dependent variable with enough sensitivity. In the GRE prep course example, perhaps taking a prep course improves people's scores by 10 points. If you were using a pass-fail measure, or even groups like high, medium, and low, you wouldn't detect the change. Your best bet is to have very detailed, quantitative increments instead of just 2 or 3 levels. We'll discuss ceiling and floor effects, manipulation checks, and design confounds on the next few slides. Ceiling effect. This occurs when the participants' scores on the dependent variable are clustered at the high end. For example, giving college students a simple addition test. For example, suppose the researcher manipulated anxiety by telling the groups they were about to receive an electric shock. The low anxiety group was told to expect a 10-volt shock, the medium anxiety group was told to expect a 50-volt shock, and the high anxiety group was told to expect a 100-volt shock. This manipulation would probably result in a ceiling effect because expecting any amount of shock would cause anxiety, regardless of the shock's intensity. As a result, the various levels of the independent variable would appear to make no difference. Floor effect. This occurs when the participants' scores on the dependent variable are clustered at the low end. For example, if a researcher really did manipulate the independent variable by giving people no money, 25 cents, or $1, that would be a floor effect because these three amounts are all low. They're squeezed close to a floor of 0. Sometimes ceiling and floor effects can be the result of a problematic independent variable, as in the money and mood study, in which all three levels of the independent variable were very low amounts of money, none, 25 cents, or $1. Poorly designed dependent variables can also cause ceiling and floor effects. If you look at the graph, it's an example illustrating a ceiling effect and a floor effect of the dependent variable and how that can obscure group gender differences on the independent variable. A manipulation check is a second dependent variable included in a study to make sure the independent variable manipulation worked. In the manipulation check depicted in graph A, it appears that the anxiety manipulation didn't work, as the three anxiety groups self-reported very similar levels of anxiety. In graph B, it looks like the anxiety manipulation did work, as it seems to differentiate the three different independent variable groups as would be expected. A design confound can counteract the true effect of an independent variable. For example, in the GRE study, perhaps that test prep group was also under additional pressure to perform well on the GRE. As a result, they were actually receiving test prep and pressure, while the no test prep group didn't have test prep or pressure. The added pressure that was applied is considered a confound. However, it didn't work in favor of the test prep group. It worked against them by lowering their scores. Another cause of a null effect might be that there is too much within groups variability, also known as noise, error variance, or unsystematic variance. Having too much noise can get in the way of detecting between group differences. If you look at the two graphs, you'll notice that the within groups variability is larger in graph A than graph B. You can see this by examining the length of the error bars in the bar graphs or by examining the spread of the individual scores in the scatter plots. Notice how having more within groups variability obscures the group differences. Let's look at the different causes of too much variability within groups. Measurement error, individual differences, and situation noise. Measurement error is any factor that can inflate or deflate a person's true score on the dependent variable. For example, a man who is 160 centimeters tall might be measured at 160.5 centimeters because of the angle of vision of the person using the meter stick, or he might be recorded as 159.5 because he slouched a bit. The goal is to keep measurement error as small as possible. Some solutions for reducing measurement error include using reliable, precise measurements. Measurement errors are reduced when researchers use measurement tools that are reliable. Internal, inter-rater, and test-retest reliability are important here, and that are valid or of good construct validity. We can also measure more instances. If researchers can't find a measurement tool that's reliable and valid, then the best alternative is to measure a large sample of participants. Random errors will cancel each other out with more people in the sample. Another source of within-group variability is individual differences. Some people are faster runners than others, some are smarter, some are funnier, and so on. In the graph, you can see how participants who received money were slightly more cheerful than those who did not receive money. But there was a lot of overlap in the two conditions. Thus, the individual differences within each group obscured the between groups differences. There are two solutions for reducing the effects of individual differences. First, we could change the design. Use a within groups design instead of an independent groups design. When you do this, then each person receives both levels of the independent variable, and individual differences are controlled for. It's easier to see the effect of the independent variable when individual differences aren't obscuring between groups differences. You can also use a matched groups design. Pairs of participants are matched on individual difference variables, and it's easier to see the effect of the independent variable. The second solution is to add more participants. If it's not feasible to change the design to a within groups or matched groups design, then try adding more participants. This will lessen the effect that any one participant has on the group average. Situation noise. This is an external distraction of any kind that obscures between group difference and causes variability within groups. This includes smells, sights, and sounds that might distract participants and increase within groups variability. It adds unsystematic variability to each group situation by controlling the surroundings of an experiment that might affect the dependent variable. A way to reduce situation noise is to test participants in a quiet room with no outside odors, distractions, and so on. Another name for all of these solutions is called power. Power is also an aspect of statistical validity. For example, if GRE prep courses really work to increase GRE scores, then the study will detect this difference. Power refers to the strength the study has to detect such differences. Studies with more power can detect even small effects. The figure here illustrates this with a light as an analogy for statistical power. Not having very much power is like trying to find an object in a room lit by a candle. You probably won't be able to find small objects by candlelight, but you could find larger objects. Having high statistical power is like having a flashlight. It's easy to find even small objects in a room lit with a bright flashlight. When an experiment results in a null effect, what should we conclude? Firstly, we check for any of the obscuring factors we discussed in this chapter. If any of these factors could have been a problem, that could explain why the experiment showed a null effect. We should attempt to correct the errors and repeat our study. On the other hand, if the study was powerful and precise and still showed a null effect, we should still report that result, even though it may be somewhat disappointing. It's important to remember that null results are just as valuable as the other studies testing the same question and are important to consider among the full body of evidence. A null effect in a study can be just as interesting as a group difference when studies are conducted with adequate power. While null effects are becoming increasingly likely to be reported in scholarly literature, in the popular media, you'll rarely find null results. The popular press focuses on group differences, yet often fails to see the value of null effects in research. It can often be just as important to demonstrate that a specific treatment did not have an effect as if it did. Just as we would want to know when a treatment would help someone, We also wouldn't want to think it might help someone when it really doesn't.